should be taken too seriously, but I view it as a very good sign for the LHC that Switzerland just beat Spain.
What was the score? 1-0.
So the Higgs thing this time might not prevent yourself.
All right, so with that thought, let's get started. So last time, I was in the process of emphasizing some very important things about QCD, which are not generically true of QCD-like theories. That is to say, if I consider theories with different numbers of colors and different numbers of flavors, some very important facts about QCD, obviously asymptotic freedom, but also confinement, are not completely generic, common, but not generic. Therefore, being able to do things like use things like parton distribution functions and factorize off the non-perturbative physics of the proton from the perturbative parton-parton scattering that we actually want to study in order to actually produce, for example, supersymmetric particles and see what they're like. These are not to be taken for granted. The fact that the hadrons of QCD look the way they do, that we have light pions, and that therefore pretty much everything we measure in these detectors are pions or kaons, a few protons and neutrons, because everything else falls apart right away, down to those particles. That's not generic. Other theories can have a whole bunch of heavy hadrons, which are all relatively stable, and no light hadrons at all. So all sorts of complexity in quantum field theory. And the last and maybe most important and subtle point has to do with parton-hadron duality. Now, this will have two stages. I will discuss it naively today, and then we'll go on to other topics which we need to cover to some degree to help to put things in perspective for Jason. What I will do tomorrow is I will do this properly. And you'll see the difference is important and deep. But nonetheless, let me start with this sort of naive view, which will still carry a lot of interesting information in it. So reminder, what we're dealing with is the important things about QCD is that 1 over NC is a third, and NF light over NC is order 1. And that affected many different things, and it will also affect parton-hadron duality. Now, if we do something in the Large Hadron Collider where a proton-proton collision occurs, and some particle which might be, in this case, an on-shell Z boson, or maybe just an off-shell gluon, but I'll focus on a colorless particle to keep things simpler. So some colorless particle is produced that then turns into a QQ bar. What will we observe? Well, as you all know, the Q and Q bar turn into a bunch of hadrons, a jet. Each of them turns into a jet. And that jet then gives us some charged particles, which give us tracks in the detector, as you heard yesterday. And also, both the charged and neutral particles leave energy in the calorimeters. And from that, we can measure the energies of the jets using methods that will be discussed today. And from that, reconstruct what the invariant mass of this pair was and show that it's equal to the Z mass, for example. OK, well, that's all fine as long as this is true, roughly. Okay? As long as the momentum of the jet has something to do with the momentum of the quark. And if that weren't true, well, you'd have a lot more trouble figuring out what was going on. And so that is what you might call a parton-hadron duality. The short-distance parton gives us some, turns into the total momentum of all these hadrons. This is not obviously the case, and in fact, there are many theories where it's false. But it's true in QCD. Now, why is that? Oh, before I say anything about that, let me make a couple of comments first about these jets, which we'll come back to more tomorrow. So if we take a look at where the energy is deposited in eta and phi, and we take the barrel of the detector and we unwrap it the way we did yesterday, so we have a rectangle here where phi runs 0 to 2 pi periodically, and eta is the pseudo-rapidity, then what we will see is two blobs of energy where these hadrons enter the calorimeter. And of course, they're not dots. They're blobs. They have a size. They don't fill the whole calorimeter. They're not dots either. What sets that size? Well, there's a calculation you can do, and we'll talk about a little bit what goes into that calculation. I won't do the calculation, but you can find it in a good QCD book. And not surprisingly, the size of a jet, the delta r, remember that r is the distance metric on this, is the linear distance on this plot. Delta r, the radius of a jet, is set by what? What do you think it's set by? What could it be set by? Momentum of the jet. Well, okay, I mean, this is actually an angular size, so it's dimensionless. So momentum over what? Well, so momentum over energy? Sorry. No, that's not what you mean. I mean, the momentum and the energy is the same, so basically. So what sets the size? What could set the size? Well, gamma of what? Quark? You know, if you look at these things, delta R is of order 0.4. It's not tiny. It's not obvious. Okay, well, the answer is that it's set by some complicated function of alpha s itself. All right, so it's set by alpha s, not some simple function. It's not like it's just equal to alpha s. It's more complicated than that. But it can't be just alpha s. That doesn't make any sense. If I considered a generic theory, it couldn't be alpha s. Why can't it be alpha s alone? It has to depend on something that's over here. Tell me why. Well, the answer is the size of a jet is calculable. That means it's calculable in perturbation theory. If it's calculable in perturbation theory, it's not set by alpha s alone. What's it? The 't Hooft coupling. Because perturbation theory is an expansion of the 't Hooft coupling. Alpha s and c. That's important because what that's going to tell you right away is that if I make alpha s and c big, if I go to a theory that actually is described by ADS-CFT in perturbative gravity, the jets are going to get very fat. And you might worry they're not going to be there at all. And they're not there. Right? So first lesson is just simple as that. If you work with the largest of coupling theory, you won't see jets. This was proven recently by Maldacena and Hoffman, but known to various people, and I used it in some models prior to their work that you might be interested in someday. But anyway, that's an interesting point to keep in mind.
So the momentum doesn't matter at all in setting this?
Well, it does, but only in the sense that alpha s runs. And so, in fact, as you go to higher and higher energy, the jets get a little narrower. But that also depends on exactly how you measure them, so it's a little tricky. But roughly speaking, they're not changing in size that quickly. Okay. On the other hand, if you look at data from 25 years ago, back at much lower energies, the jets were a lot fatter. And in fact, in the mid-70s, there was a question, will we see jets or not? Because they were so fat, and the detectors were so preliminary that they couldn't really tell. And it was very important when they finally started to see, oh, these events are not spherical. There really is a tendency for things to be jet-like a little bit. Well, now we just take jets for granted, but you can look at the old data. It's not like that. Okay, and that's not the only reason why it's important to think about the specifics of QCD. And what I'm going to talk about today is that hadronization, the process by which hadrons actually form in these jets, is also not to be taken for granted and depends on these quantities. And so to understand that, the best language is, in some sense, since you guys all have seen, either know string theory or have seen some lectures where string theory was used, it's best to analyze this from the point of view of string theory. And, of course, the details of how this works depend on exactly what theory you're talking about and what value of the coupling. But I'm just going to focus on the NC and the NF dependence. And for that parametric dependence, using string theory language is convenient. So supposing we have a Z boson that decays to two quarks. Let's even say they're bottom quarks, so they're heavy, relatively speaking, compared to the QCD scale. So they move apart inside the proton. So in this first picture, the proton's very big. We've just produced them. Okay, now we look a little bit later. Now the confinement scale on this is about the width of this tube. What has happened? We have a bottom quark and an anti-bottom quark, and there's a flux tube between them that's trying to form. That is, of course, the confined flux of the gluons, the chromoelectric flux. And we know that what happens is that pairs of light quarks appear inside of this strong field, and this flux tube breaks up into a bunch of little droplets, which are hadrons, each of which is a quark-antiquark pair typically, with maybe a few baryons in there. And most of them are heading this way or heading this way, and there are a few sort of low-energy ones going out the side. And that, of course, is what leads us to the picture which is shown up there. Now, what is involved in this? Well, it all has to do with the quark-antiquark pair production, which has to be fast. Suppose, for example, there were no quark-antiquark pairs at all. Supposing all you had was heavy quarks, really heavy quarks. Supposing the bottom quark was 1 billion GeV. You just produced a pair of them. And now you've got energy here in this flux tube, which is down in the few hundreds of GeV or something. You don't have enough energy to produce a bottom quark pair, so what's going to happen? Well, the flux tube can't break, so the bottom quarks are going to slow down and turn around and come back. And they're going to swing back and forth because the string can't break. All right, so it's important that this process is fast enough that the process itself doesn't steal a lot of momentum from this bottom quark and move it somewhere else. Because if there's time for the momentum of these quarks to get rearranged by the strong non-perturbative dynamics, then it's not going to be true that what comes out in the general direction of one quark is actually the momentum of the quark when it was produced. And parton hadron duality will be lost. Now let's see how easy it is for that to happen. So to do that, let's consider 3 cases in string theory. So here's a string. Let's not care too much about what's on the ends. Let's look in the middle. So it's a string. It's excited. It's got some wiggles on it. And if this is a string theory with the exception of the heavy things on the ends, is basically a closed string theory. So that it can't break, at least not very fast. How is it going to lose energy? The only thing it can do is radiate closed strings. So what it will do is it'll pop off a closed string at a cost of the closed string coupling constant, well, for a rate squared, which, if you know your NC counting, means there's an order of 1 over NC squared here. Now, from the ADS-CFT correspondence, how would you view this? If you took an ADS-CFT version of a QCD-like theory, how would you make it? Well, I don't know if anyone discussed that specifically, but it's easy to understand from the things that you've learned. So here is ADS. Here's the boundary of ADS at r equals infinity. If we really had a pure ADS space, we'd have a horizon down here. But if we have confinement, what happens is the space is somehow cut off in a smooth way. And there's some complicated region down here where the metric's much more complicated, and a minimum radius. And what I'm going to do is I'm going to put a D7 brane. I'm assuming we're doing ADS5, so we started with a bunch of D3 branes. I'll put a D7 brane in there. And if there were D3 branes down here, then a string hanging between the 7 brane and the 3 brane would carry fundamental charge under the SUN gauge group. It would be like a quark. Okay? And because the 7 brane is far from the minimum here, it would be a heavy quark. So this is our model of a bottom quark. But it can't end down here because the space is a minimum. If there were a horizon, it would just disappear into the horizon, but there isn't one. So what happens is, if I have a quark and I have an antiquark, they have to somehow be joined by a string which sits at the bottom there, and that's our flux tube. So this string is our bottom quark, our flux tube, and our antiquark. And the only way this thing can lose energy, if it's got some excitations, is by popping off, essentially, gravitons. And that costs you a closed string coupling constant squared. Now, it's very different if I have a massless quark in the game, or a light quark. Because if I have a light quark, that corresponds to putting, in addition to the heavy quark, D7 brane, some additional D7 brane down here. So now what I have is a string which is hanging down in the same way as before, but it can break in a new way. It can break as shown above. Right? Here's a D7 brane, here, or a D brane of any sort, in fact, and here's a string. It can just break like that with a cost, which is the open string coupling constant, squared, which is the closed string constant, which is 1 over NC, faster by a significant factor. So just the presence of one light quark makes the hadronization process much quicker and also much simpler, because here you have to figure out how these closed strings are going to come off. Here, you just break the string in the middle in some very simple way. And you do it again and again, the thing just falls apart. And you end up, eventually, with lots of little open strings floating around down there, which correspond to mesons, plus light quark mesons, in addition to some mesons that involve a heavy quark and a light quark. That's the picture in ADS. It's qualitatively correct. Quantitatively, of course, it's wrong, but qualitatively, it's the right picture. And the other thing is that if I have multiple D7 branes, I won't bother to draw it here, but it's clear if you look here. If I have multiple D7 branes, then there's multiple processes which can occur, which are all of the same type. They don't interfere because they're different, but they add. So in this case, you get a factor of G open string NF, where the NF is the number of D7 branes which are down here, the number of light ones. So there's an enhancement. So compared to this situation, a theory with NF light over NC of order 1 has a much more rapid process by which the strings fall apart. Qualitatively much more rapid, parametrically much more rapid. Now this is really critical because it makes sure that there isn't time in this process for the string to pull back and change the momentum of the quarks. And therefore, the quark momentum and the jet momentum match. Essentially, hadronization has almost no effect. It's not that hadronization is important in the formation of jets, which is what most people think. Hadronization is unimportant in the formation of jets, and that's crucial. It's a pass-through filter. It just lets the momentum go through the QCD scale and right out the back. It just converts the partons into hadrons without screwing everything up. And that is because in QCD, well, at least NF isn't 0. And perhaps even it's important that NF over NC is of order 1. Okay, any questions? Yeah?
Was the scaling guessed before we had the ADS?
Oh, sure. This was known. I mean, all these scalings were known to 't Hooft in 1973, 4? In some sense, it was hinted at earlier because, of course, the first models of QCD were strings. Right? String theory is the first, before we knew about quarks, models of mesons as open strings were already around. So in some sense, it was known earlier than late 60s, early 70s. I'm not sure who was really responsible. It goes back many, many, many years. This ADS-CFT is convenient for you because you know this. Okay? But you don't even really need ADS-CFT, right? You could just see this. This is just be flat space string theory. So four-dimensional strings at tree level have this property. Other questions? Yeah.
From the string picture, what pulled the string down to the IR initially?
Oh, the really important thing about ADS to remember is that there's gravity. Gravity pulls this way, from the boundary down to the horizon. Right, and that's the curvature of the ADS space. Pulls every, and that gravity in the ADS picture is physically the same thing which in ordinary field theory is what makes everything want to expand. Right? If I put a lot of energy in one place, it wants to grow. That's the same statement. This is an ADS space. If I put something here, it wants to fall. That's the physical intuition you need to carry with you. Other questions? Okay, now, there's a certain really amazing irony to this. I mean, we as theorists would really, we really view, and I think correctly, we view QCD as sort of the worst possible case. And 1 over NC of order a third and NF light over NC of order 1. I mean, think about what we can actually do in ADS, okay? The best theory is just, don't have to deal with these D7 branes. We just have large NC, really large, so that everything's nice and perturbative, from the bulk point of view. And that would, that's at least classical, or semi-classical from the bulk point of view. So large NC is great for us. And then if you put the D7 branes in, well, life gets more complicated if you try to calculate with these things. But at least if there's just one of them, they don't back react on the geometry. So you can still take large NC, calculate the geometry, and put the D7 branes in as probes of the geometry, and it's still a pretty simple calculation. That's NF light over NC, much, much less than 1. And QCD throws at us the worst possible case, where NF light over NC is of order 1. And so therefore, if you want to calculate an ADS-CFT, a theory like that, and its properties, and get the hadronization to be qualitatively right, you have to put lots of D7 branes in here, which is tricky, or do some other construction, which is what you really need to do. There's all sorts of back reaction, and we don't really know how to handle this well. It's a mess. So for theorists, this is terrible. This is why we've taken so long to figure this theory out. But from the experimental point of view and from the physics point of view, that is the point of view of actually learning what nature is about, it's the best possible situation. If, in fact, we had dealt with a theoretically simple situation, it would have been a disaster. Because we wouldn't be able to measure this process where we make supersymmetric particles and quarks come out, because the quarks wouldn't turn into jets. We would have no way of accessing the quark momenta. They'd be all jumbled up. If you think about a pure Yang-Mills theory, for example, where there are no quarks, and you just have glue balls, and you imagine the properties of a large glue ball collider. Okay, so here you have a large glue ball collider. Inside that glue ball collider, you have gluons scattering, and out come two gluons. What are you going to see? Well, the two gluons are going to make essentially a closed string, which is going to go out and come back and spit off little pieces, and it's going to, little pieces are going to go flying everywhere. And those momenta are going to be completely scrambled. The only thing you're going to be able to figure out is the total energy of the collision, but you're not going to be able to figure out where those quarks went, where these gluons went, even though there was asymptotic freedom at the scale at which that process took place. So you really must not take this fact for granted. It's actually fortunate for physics that QCD is hard, because it's what allows the perturbative physics to get through the hadronization scale without getting screwed up. Any questions? Now we're going to turn to a different set of topics. The first one is to just talk a little bit about the process. And again, I'll come back to this tomorrow in a little more detail. But the first thing I want to do is I want to talk a little bit about the process of doing measurements and calculations. This is not something which most of you here are going to actually do, but it's important to understand why it's done the way it's done. And also to appreciate what goes into it and the amount of physics that goes into it as opposed to what your impression may be. So let me first start with some very, very simple things that many of you may have already thought about. So let's consider a case where instead of making quark-antiquark goes to Z goes to quarks, let's just make sure so we're all on the same page. Suppose we have a very simple decay where the Z goes to electrons. How do we figure out that we made a Z? Well, that's easy. In that case, we just have two isolated tracks in the detector, which leaves some energy in the electromagnetic calorimeter. And those are identified as electrons. We can measure their 4 momentum very well. Well, we actually measure their 3 momentum and infer their 4 momentum, since we think they're electrons. And then we just add the 4 momenta of the two particles, square it, and see what it is. And if it's equal to mz squared, it was a Z. Now, of course, it's not that simple because the Z has a width. And also, this process interferes with the process that involves a photon. But we can predict the square of the sum of these two diagrams. So we know what the matrix element squared is. We know the Parton distribution functions for these quark and antiquarks to some degree. And so we can predict what the distribution of the invariant mass of the E plus E minus should be. And, of course, there'll be a peak at the Z. But then there's a tail. Now, if we were doing an E plus, well, let me just say the answer. Okay, so it looks something like, well, that's a little bit too sharp. But it looks something like that. There's a big growth down here because there's so many low-energy quarks and antiquarks that it's easy to make a photon into electrons. But what you'll do, of course, is you won't look at the ones that have really low energy down here. You'll just sort of focus on the ones here, and that tells you if you made a Z or not. Yeah?
So you said you couldn't measure the energy, but can't you just see how much the calorimeter heats up?
What I said was you're measuring the 3 momentum, but I was sort of cheating. What you're really measuring is the angle and the energy. The angles and the energy. How do you make sure you're choosing the correct electron pair? In most collisions, you only have two, if you have any. And most collisions don't make any electrons, or at least none of any significant energy. So usually it's pretty easy to figure out. So, I mean, yes, but let's not get hung up on details. We want to get to the important stuff. So one thing, however, I've done here is I sort of drew this as though the Z boson was moving along the beam pipe, which would be true if nothing else happens but what I drew here. But of course, lots of other things can happen. For example, a gluon can get radiated off of here. So then we have the Z moving a little bit and recoiling against the jet, which may not be very hard. So then our event will look a little different. One of the electrons may be significantly more energetic than the other, and there may be some additional tracks from the jet. Now that doesn't really matter, because this formula only cares about the momentum of the electron and the positron, and it doesn't care if there was something else in the event. That's nice. Okay, so Z bosons are pretty easy to identify because you don't care what else happened. Slightly more complicated and more interesting for that reason is if you have a W boson produced. So let's just take the same type of process. QQ bar goes to E minus neutrino. Now, of course, what you see is that. And you measure the momentum of the electron transverse to the beam, and you measure the energy of the jet transverse to the beam, and you see they don't add up. There is missing transverse momentum here. And that, of course, tells you that probably there's a neutrino. Or you screwed up, which happens sometimes. Okay, but let's assume it's a neutrino. Now, the question is, how do you figure out that this is a W? Well, if there were no jet there, if the W was moving right along the beam pipe, then you would be able to, then you would know, if I looked at the transverse momentum of the electron, what would I know? Well, the maximum transverse momentum that the electron could have, if the W is moving on the beam pipe, is easy to compute. Go to the W rest frame. That's moving this way along the beam pipe, or it's moving that way along the beam pipe, but it's moving this or that way. So just sit in that rest frame. In that rest frame, the electron goes out at some angle. The maximum transverse momentum is this way, and that's Lorentz invariant. So now I can go back to the lab frame. The maximum transverse momentum that the electron can have is mw over 2. Is that clear? You have to account for the width, so it's spread out a little bit. But basically what you would see is something that would do something like this. Now, this is not what we observe. It's not what we observe because of this, because this happens all the time. Right? Emission of a gluon is off the initial state is very common. And so that has a tendency to kind of smear this thing out. Now, in the notes, I won't go through it here, there's a trick for for tightening this up by using a slightly different variable. It's called the transverse mass. It's a cute theoretical trick. Nice little bit of math. You sort of view the problem as effectively two-dimensional, and you remove the right information, everything cleans up a little bit, at least to first order, in the momentum of this jet. Okay, but I leave that to you. It can be done. You can clean that back up a little bit. But if you want to, for example, measure the mass of the W well, you need to know precisely how it cleans it up. You need to know what the shape looks like. And to do that, you need to predict this process, and the process where two gluons get emitted, and anything that contributes significantly to the kick that the jets apply to the W, and thereby to the electron and neutrino. Okay, now, so this is where it gets a little interesting. So here's 3 questions you might want to ask that go from simple to hard. First is, how many W events, where the W goes to E nu, will actually be produced at the LHC? That's just an overall rate question. Well, there's a first order diagram. There's the diagram where gluon gets emitted. That has to be included as well. There are loop corrections you may need to include from, let's say, loops of gluons going in there. There's some hard calculation to do, but it can be done to some accuracy, which is actually quite high now. It's done to essentially two-loop order. Now, another question you might ask, which is a little trickier, is what is the actual momentum distribution of the electrons? There you have to account for the way in which the W decays. I mean, you have to keep track of where the W went, but also what its spin was. So it's a little trickier now, because you've got to keep track of angles and to get the momentum distribution of the electron. And the third question you might ask is, how many of those events are actually going to get into Jason's plots? How many events are you actually going to see? Now, that's important, because at some point, we're going to actually look at plots that the experimenters are going to have, and we're going to try to interpret them. So we need to account for the fact they don't see all the events. Now, what are the difficulties with these three questions? Well, we can almost, as I said, we can almost calculate the total rate, although we have to account for these extra diagrams, and it's a hard calculation, but it can be done. The next thing we have to do, when the W gets kicked sideways by these gluons, what it's doing is it's essentially, well, if there were no kick, it's this first plot. The more kick there is, the more there is a tendency for the electrons to leak out on this tail. Now, you may say, that's a little tail. I don't really care about it. But if you're looking for new physics at high energy, where are you looking? You're looking in the high energy region. So these tails matter. And they're hard. And finally, and this is the real killer, we actually want to figure out how many of these events get detected. We have a bunch of things we have to account for. First of all, the detector has a shape. If the electron goes too far forward, it doesn't get tracked. There are cracks in the detector. Those are probably minor effects. But, I mean, there are things like that you have to think about. You don't measure all the electrons because you have to avoid backgrounds and effects from weird things that can happen in the detector. You don't want to look at very, very low energy electrons. And worse than that, you do have to trigger on these events. You're going to hear more about that. If the electrons are down here too far, you won't even trigger on them. So there's some region below which you won't include these. You need to account for that. So you also need to know this region well. And finally, these kinematic distributions are complicated in eta and phi. You have to know them really well. So it's not enough to know the PT distribution. You have to know the eta and phi distribution to know when the trigger is going to be have an impact, or whether the geometry is going to have an impact. There's other things you could worry about, too. None of this can be done by sitting down with a piece of paper and doing an analytic calculation. Right? Obviously, this is just, you cannot do these integrals. You've got integrals over x1 and x2 to do for the PDFs, and you have integrals over PT and eta over PT and eta to do, and there are complicated cuts and considerations, and it cannot be done by any human integrator. So it is, unfortunately, absolutely required for all calculations at the LHC to use a computer at some point. And that computer, the computer program which is involved, has to not be some sort of just little machine. It has to incorporate all of the important physics that's supposed to be accounted for. So it has to be written by really good physicists who understand all the different issues. And the computer programs which are out there require the work of many experts. So they're also not to be taken for granted, both because they have a lot of physics that goes in, and because there's always some compromises that were made, and sometimes it's important to know what those compromises were if you're dealing with something new. So these are called Monte Carlo, because they involve random number generators, event generators. They're supposed to make events that look like this, simulated, and then allow you directly to account for all these geometrical concerns and so forth. And they go by various names. I've written some of them down. All of them contain some of the calculable physics and also models of some of the physics that we can't calculate, such as the underlying event, all that spray of debris, which sometimes is important, so it needs to be in there. Or the formation of jets, some of which we can calculate, some of which we can't. And I'll talk about that more in a minute. There are programs which, in particular, Pythia, Herwig, and Sherpa are among those programs, which try to model what happens to the debris of the protons when they come out. Cannot be calculated. It has to be modeled. It has to be modeled reasonably. How do you test whether the model is reasonable? You go and you look at the data. It's a matter of tuning to the data. And that's why measurements of the underlying event in the early days of the LHC is so important, because you've got to take these models that are going to produce all this noise that we have to account for and fit them to the data. We theorists are not smart enough to do these calculations ourselves, so we rely on nature to tell us what's going on. Okay? Now, on the other hand, we also need programs which can calculate things like this and do it well. That is, say, do the tree diagram with no gluon, do the tree diagram with one gluon, maybe even do the loop calculation. Well, we don't have those programs yet, but they're coming. And certainly sew them together to get a reasonable-looking, physically motivated distribution, which is not going to be perfect because our calculational techniques are not perfect, but they have to be the top of the line, the best that we have. Or we're going to get confused about things like tails of distributions where we're looking for new physics. So the best calculators in the world are involved in writing computer programs that will put all the information that we have together into programs like MadGraph, Sherpa, AlpGen, CompEP, to make sure that our calculations of standard model processes are as good as they can be. They also are involved in helping us calculate the signals. But believe me, the signals, most of the time, are the least of our worries. Signals are relatively easy because you often don't have to account. Sometimes you do. Often you don't have to account for all these extra effects. But the standard model, you need those tails really well. You need to do things with very high accuracy and precision. Now, the other thing which some of these programs have, in particular Pythia, Sherpa, and Herwig have, and maybe a couple of others, is a model for jet formation. How do you turn a quark or a gluon into a jet? And that involves 3 stages. In fact, I wrote them in the order in which they come, but in some sense it's easier to work backwards. What we see in the detector is a lot of pions. Not all those pions were created in the breaking of the string. When the string broke, some of these particles were pions. A lot of them were rho mesons, or omegas, which are also quark-antiquark pairs. They're heavier. And what do? They decay to pions. So we've got to account for all those decays. So there's a model for hadron decays that accounts for all the different decays. Everything we know about hadrons is in there. Then there's a model for hadronization for this process. How did you get the hadrons in the first place? Well, that we just have to model. We don't understand it. We can't calculate it. We make a reasonable model, which is take a string between a quark and antiquark pair and start breaking it in some reasonable way. Now, it's actually a little more complicated than that, but basically that's the idea. It's this picture. It's this picture, if you like. You just start putting quark-antiquark pairs in the string, you break it apart. So if you want to know what hadronization is about, it's string theory in Pythia or Herwig. Herwig is a slightly different model, but that's what Pythia does. These are models which have to be fit to data. So again, you go to the E plus E minus collider at CERN from 10 to 20 years ago. Tremendous amounts of data were taken on Z bosons that go to jets. And you study all of those processes in great detail, and you see if your hadronization model works or not, and you tune it until it does. It's a model. We don't know if it's exactly right. We don't know if it'll become problematic as we increase the energy. We have to keep an eye on that. And finally, there's the thing which is the most important for the formation of a jet. And I've told you today why it's the most important, because hadronization is a pass-through filter. The most important thing is what happens before hadronization. And that is the process known as showering, which is a largely calculable process that we will talk about tomorrow. It is a perturbative, or if you like, resummed, an infinite resummation of a perturbative process. And the way in which a quark goes to a quark or gluon goes to a jet involves that process. So that's real detailed QCD, and that's in Pythia and Herwig and Sherpa. Of course, it's only there at tree level. We'd love to have some corrections to that. So there's still a lot of QCD to do to improve those calculations, which are not models. They're calculations of things that really happen in QCD. Okay, any questions about that general point? So let me just re-say it while you're thinking of questions. The basic point is, you start from theory. You want to end up with data. In the middle of this, you have to make a prediction. Okay? Making the prediction involves these computer programs. There simply are no predictions at the Large Hadron Collider without using a computer program. And you've got to use good ones and know how to use them. Yeah?
So in these hadronization models, do you know approximately what's the number of continuous parameters?
The question is, how many parameters are in these hadronization models? I'm not an expert. I don't know. But you can look them up. I mean, they're described in detail in the Pythia manual, the Herwig manual, because, of course, people want to know exactly what's in it. So they describe it. Okay. Any other questions about this process?
What's the difference between these different models, Pythia and
Pythia and Herwig? Let me not go into that just for lack of time. I just would rather not. I mean, they differ in detail, and they differ in philosophy. They're tuned to data in the end, so it's hard to say which one is right. They all fit the data, of course, because they were tuned to fit the data. Okay. I mean, the thing I just want you to take away from this, I mean, there is sort of a sense, I think, in the community, for those who are not experts, that these Monte Carlo programs are just, you just hit return and you get your answer. And they're just ways of encoding these simple calculations. No, there's a tremendous amount of physics that's in them. And really non-trivial physics. If you study why it's possible to even write a computer program to do all this stuff, it's not obvious that it's possible at all. To prove that it's possible required some very great physicists working on this stuff in the 70s and 80s to show it could be done. So don't take it for granted. There's a lot to be learned there. Okay, now I turn to flavor. So any last questions on this? All right. Now, flavor physics, of course, is a huge topic in the Standard Model, and I won't do it justice. But there are some important things to keep in mind that will also relate to some of the things I'll say. So what I'm going to do first is make some general remarks on flavor and remind you of things that I'm sure you all know. And then I'll say a few things about the third generation in particular. Now, why would I talk about the third generation? Well, that's in some sense fairly obvious. The third generation is heavy, and therefore if there is new dynamics at the LHC scale, which has something to do with flavor, we expect the third generation to be most sensitive to that. So we are really interested in being able to measure, in being able to identify tau leptons, bottom quarks, and top quarks. They may be our window into the new physics. There's lots of models of new physics which dominantly produce taus, b's, and tops. So now one of the reasons to talk about flavor and how it works is to see why it's possible to do this, why it's possible to identify these particles in some way. And that's not trivial. Remember, yesterday we talked about the fact that for up quarks, down quarks, and strange quarks, and gluons, they all make jets that look pretty much the same. So we can't identify them. It's a good thing we don't really want to know the difference between a down and up quark that often, because we wouldn't be able to. But fortunately for bottom quarks, we can. And that has very much to do with the specific properties of flavor in the Standard Model, which then motivates me to review it. How many people think they could sit down with a piece of paper and no book and rederive where the CKM matrix comes from? I'm glad Nadi raised his hand. Okay, I mean, it's not trivial. I'm not going to do it. But I'm going to remind you where it comes from. It's something that's good to be able to do because, again, a complete understanding of the Standard Model means you can sit down and figure out what is the transformations that you need to do that show that the CKM matrix only shows up for the left-handed quark fields and in the couplings to the W's. And there is no such matrix for the couplings of any field to the Z boson, to the gluon, or to the photon. Okay, it has everything to do with what I said about rotating mass matrices at the very first lecture. But I'm not going to go through that. Let me just remind you, though, it's this fact that the Z's, the photons, and the gluons don't change flavor for either quarks or leptons, for that matter, at least at tree level. And any violations of that statement are very, very small from experiment. because of that, the W boson mediates all decays of fundamental particles. So tau, for example, which we'll come back to in a moment, is always decaying to a new tau and an off-shell W, which is then, it's in turn either going to a lepton and neutrino or to quarks, although the tau is so light, 1.77 GeV, that to talk about quarks at this point is not very useful. So the really important thing is it goes to a number of pions. And the number of pions could be 1, 2, 3, or it could be a row. It goes to some hadrons, 1 or 3 of which, actually, let's get the signs right. Maybe 3 of which are charged. So when a tau decays, what does it make? It makes a lepton, or it makes a couple of pions. And if you think about it, the invariant mass of the things that you observe can't be larger than the tau mass. And so this actually forms a jet with a very small radius, a much smaller radius than the typical jet. Well, I would erase the, right? But the delta R for a typical jet is 4.4. This little mini jet, well, not really a mini in the sense of PT, but it's a very narrow jet, can be identified to some degree because of the fact it's so narrow, and it has so few tracks. So that's important for tau ID. Now, the bottom quark, on the other hand, for example, can decay in a similar way to it. Oh, I'm sorry, I left one thing out. Let me say one more thing about the tau. The other really important thing to notice about the tau, sorry, there's a neutrino here, is that there's always a neutrino. So you never, ever measure the momentum of the tau. You always lose some of it. You can measure its direction, because this jet is so narrow, but you don't know the momentum. That's important. And problematic, but there's some tricks around it. All right, when a bottom quark decays, it will decay typically to a charm and a W star. Sometimes it will decay to an up quark and a W star, but that's rare. And again, the W star now will turn into an L nu, or it can turn into a bunch of hadrons, more hadrons now, because just there's more energy available. Nadi?
What is the amplitude for an even number of pions versus odd number of pions?
I can't answer that on the fly, because you've got rho mesons in there, you've got A1s. It's tricky. The important thing is that you only get 1 charge track or 3 charge tracks. The number of pi zeros, I don't even know what we know. So I leave that to, it's a good question. I'll see if I can find out for tomorrow. In the detectors, actually measuring the number of pi zeros is difficult. Measuring the number of tracks is easy because the tracker has very high resolution and you pick it up. Yeah, I understand your question was theoretical. Well, that's what I'm saying. It's complicated because you have to account for the resonances which change the numbers. You don't think so? Okay. What he's telling me is that I'm wrong. So in the standard model, So in the standard model, processes like this one, B goes to S gamma, or B goes to S lepton pairs, which would go through a Z or photon, or through some sort of loop diagram. These are allowed at loop level. They're not zero, but they're very small. They're suppressed. They're suppressed by more than you would expect by symmetries. Okay, and I'm not going to go through those. But what's really important about this is because they're suppressed by more than you would expect, it does not take much for a new physics model to dramatically change the rates for these things. And conversely, therefore, the fact that we haven't seen that this is much larger than expected in the standard model puts a tremendous constraint on new physics models. So flavor physics, because of the absence, because flavor-changing neutral currents, as these things are called, are absent at tree level and suppressed by more than you would expect at loop level in the standard model, they're a very powerful tool for looking for hints of new physics, and they're a very powerful tool, since we haven't seen anything anomalous, in constraining new physics. And that's something we have to account for, and it constrains supersymmetric models, it constrains technicolor models, it constrains all the models. All of the new physics models have trouble with this problem. This is where the standard model really stands up and says, I dare you. Okay? model builders die every day on those flavor-changing neutral currents. All right, so all the decays are occurring through these these charged currents, the W. But even those are not so simple because there's this CKM matrix, which tells you that the probability for bottom to charm, for example, mu nu. Let me say it this way: the branching fraction for the bottom quark to go to an up quark mu nu is versus charm is roughly the CKM matrix element VUB squared divided by the corresponding matrix element for VCB, where the matrix, the CKM matrix with labels, one of which is a up-type quark and one of which is a down-type quark, is given in your notes. And that just gives the coupling of the W to an up and a B squared divided by the coupling for a charm to B squared. So we measure all these things in data, and we know what these rates are going to be. Now, it's important to keep in mind the structure of the CKM matrix, and this is why I'm doing this. The structure of the CKM matrix is that, well, zero is a bad way to do it. These matrix elements are big, and then these ones are smaller. These ones are maybe not so small. But these ones are quite small, and these ones are pretty tiny. It's almost diagonal, not quite. And that's very important in understanding a key physical aspect of the bottom quark. Because if you're looking at a decay diagram, like bottom decay, and I include here all the different decay chains here, so all the different possible final states. What's the rate or what's the rate for this process? What's it going to look like? Well, first of all, there's going to be a weak coupling constant to the fourth power. The square of this diagram will have 4 coupling constants. And then, because there's a W here, there's a 1 over mw squared in the amplitude. That means there's a 1 over mw to the fourth in the rate. And then, just by dimensional analysis, there's going to be the mass of the quark, in this case the bottom quark, to the 5th power. And finally, VCB squared. Okay, so that's going to roughly give us the lifetime for the bottom quark. For the charm quark, what is the answer? Well, the coupling's the same. The mass is much smaller. But what appears here is VCS squared. Now, VCS squared is of order 1. Whereas VCB squared is of order 10 to the minus 3. And so, because of the diagonal structure of the CKM matrix by generation, and the fact that bottom to charm is intergenerational, the bottom quark actually lives longer than the charm quark. And that is experimentally incredibly important. Because, first of all, not only does the bottom quark live longer, but it lives long enough. The lifetime here is of order, it's in the notes, but the basic, let's see, 10 to the minus 12, yeah, it's picoseconds. Okay, remember foot per nanosecond, so this is 1,000th of a foot. Right? So 1,000th of a meter, it's a fraction of a millimeter. It gets enhanced a little bit by a boost factor if this particle is moving fast enough. And the trackers at the LHC and also with the Tevatron and even at LEP were powerful enough that when a bottom quark is produced and turns into a bottom jet, which has various pions in it, but in particular some sort of bottom meson, that bottom meson will travel a distance and then decay into a few tracks, typically of order 5, 3, 7. those tracks, now this distance here is a millimeter or less, but this opening angle is big enough that when these tracks enter the tracker, they're measured with such precision that when the measurement is made out here, they can be tracked back and see that the primary collision point was missed. How do we know where the primary collision point was? How do we find the primary collision point? How do we know where it is? And see that these tracks missed? There's all that underlying event stuff. Dozens of tracks coming from that collision point. So the first thing you do when you're trying to do measurements like this is you use all those tracks. You figure out where the collision occurred. Then you look for tracks that are maybe higher energy that missed the collision point. And then you see, perhaps, even if they form a vertex. Now, this can happen for bottom mesons. It can happen for down mesons, for charm mesons as well. But because the charm lifetime is about a third of that of the bottom meson, it happens less often. So when you look for displaced tracks like this, tracks that miss the collision point, even if you don't manage to form a vertex, because maybe you'll miss most of these tracks, you won't be able to measure the displacement well, but even if you just have one displaced track, and certainly if you can make a vertex, the chances are you have a B meson in your jet. And maybe you have a D meson, but that's less likely. And rarely, of course, you just have a mistake, because tracking isn't perfect. So it might just be an ordinary jet with an error. So what are the rates for that? Well, Jason, you're going to talk about the rate fractions and stuff like that a little bit. Just the tagging fractions. Tagging efficiency. Yeah. Well, let me just make one remark because I think it's good for theorists to hear it. I mean, again, we do calculations with Feynman diagrams, okay? And then the experimentalists come along and they say to us, okay, if I look for a bottom quark using this method with sufficiently high energy, I don't have to worry about some low energy effects. Then with the tracking available at the LHC, I'll be able to identify bottom quarks about 70% of the time. Okay, this depends on exactly how I set the algorithm. I can adjust the number. But roughly speaking, 70% is about as well as you can do. And that's because some of the bottom quarks decay too early, just by statistics. And some of them don't produce enough tracks, or the tracks are hard to measure. You know, various things can go wrong. But 70% of the time, that's pretty good. If you were trying to find charm, the next statement would be bad. But if you're trying to find bottom without finding charm, which is mostly what we're trying to do, the next statement is good. You're only going to pick up about 15 to 20% of the charm quarks. So most of what you're getting is bottom quarks. There's a little bit of admixture of charm. You have to account for that because the charges are different, the behaviors are different, and okay. And then, of course, you make mistakes. If you have a light quark jet or a gluon, the experimenters will tell you, well, this is sort of a 1% effect. And here comes the translation problem between theorists and experimentalists. Okay? Very good lesson here. Always listen to experimentalists very carefully, because mistakes have been made in literature for precisely this reason. This 1% assumes that in the Monte Carlo, which was used to estimate this, the gluon did not do this. And when you calculate a Feynman diagram, you may not worry about that. For example, you may say, oh, glue, glue goes to glue, glue. That's the end of the story. It's a gluon. But there is, of course, a probability that the gluon is a little bit off shell and turns into a BB bar pair, which are on top of each other, so it still looks like a single jet. But now you have two B mesons in there, and the probability of tagging such a jet is no longer small. So you have to multiply the probability that this happens by these probabilities times 2, because there's two B mesons, and you get another % or 2, which is a big number when you've got lots of gluons around. Okay, so be careful. The lesson here is not to remember this specifically, but be careful in thinking through whether you've really communicated with an experimentalist on what it is they've measured and how they did it, because these details can change backgrounds by a factor of 3 in some cases. It's a lot. Okay. Now, finally, let me come to the top quark. By the way, the tau lifetime is also too short to measure. It's shorter than the bottom quark, although when you get enough of a boost, maybe there'll be a chance to start seeing it a little bit, but it's pretty tough. And that's just because the tau is light, and like the charm quark, it has some factor here, and when you go through the numbers, it's a little bit too short. The top quark does not satisfy this formula. But you can see that if I were to be naive and say, supposing I took a top quark which was lighter than the W, I would already learn something. So suppose the top quark weren't 170 GeV, but it were 70 GeV. Okay, it would still have to decay through a diagram like this, roughly speaking. Top goes to bottom. That would involve VTB. VTB is of order 1. So there would be no suppression. And the lifetime relative to the charm quark, therefore, would be m top over m charm to the 5th power. Sorry, the other way around. The width would be m top over m charm to the 5th power. So the lifetime would be extremely short. So top quarks decay promptly. We don't see any displacement from them. In fact, it's even stronger than that, because the top quark decays to WB with an on-shell W, because it's heavier than the top, heavier than the W. So it's a 3-body decay, which means, sorry, 2-body decay, which means it's faster. These are all off-shell Ws. They're phase space suppressions. This is an on-shell W, so it's really fast. And it's even faster than that, because the W is part longitudinal. The longitudinal part of the W is secretly part Higgs, and the top has a large coupling to the Higgs. So the lifetime is shorter than you'd imagine, and it turns out that the width of the top quark is of order a GeV or so, I forget the exact number, so short that the top quark decays before it discovers that it's confined. It never hadronizes. So to a very good approximation, the top quark is a perturbative object, which is nice. I mean, you can calculate all sorts of properties about it with higher precision than for the other quarks. Part of why we know its mass as well as we do. The other quarks, we don't know the masses very well. The top quark, we pretty much do. It's partly because of this. It also makes calculating, I mean, I've written numbers here as though we really know what we're doing here. But there's all sorts of hadronization corrections here which are important to account for. For the top, everything's much simpler. Now, what do we know about the top? Well, we know a great deal already from Fermilab, but what that tells us is the standard model description of the top is pretty good. We haven't tested everything about what the standard model says. We don't have enough top quarks yet. We will very soon, because the LHC will produce jillions of them. And I'm not going to go through as much as is in the notes. Well, it's actually not that much in the notes. Maybe I will. So the top is going to WB, and then the W, in turn, is going to an E nu, a mu nu, a tau nu, or UD, CS, and actually US and CD as well. All right, and the fractions are what's important for us. And the fractions are basically 2/3 and then 1/9 for each of these. Oh, another piece of language for communicating with experimentalists you've got to be careful about. What's a lepton? There are 3 leptons, right? Not in an experiment. Experiment, there are only 2 leptons. The tau is sort of a special case. All right? When people talk about leptons, they almost always mean E's and mu's, things you can actually see in the detector. So be careful about communication about those things. Right? So there are leptonic decays of the W, which are easy to use. There's a tau decay, which is tough to use. It kind of looks like a jet plus missing energy. And you don't always identify the tau, and there's lots of fakes. These are obviously 2 hard, clean jets. So if you make TT bar, which of course is how you mostly make top quarks. Whoops. Sorry, it came out of the holder here. So give me a second. If I don't solve this in a minute, I'll just hold it. There we go. Okay, so if you make TT bar, which is mostly what you do, glue goes to TT bar is the typical process at the LHC. You just basically have the geometric combination of these 2 things, one for the top and one for the anti-top. And so basically you have 44% of your events give you 6 quarks, 2 bottom quarks and 4 other quarks from the W's. So QQ bar, BB. And about 30% are so-called semi-leptonic events, where one top goes hadronically and one goes leptonically. QQ, L nu, BB bar. About 5% are dileptonic, where you have L nu, BB bar. And leptonic here means experimental leptonic, E's and mu's. And there's another 21% of the events that have taus in them, and they're complicated to deal with. So most of the measurements are done with this set. The leptons are nice because, well, leptons are always nice. There aren't too many leptons in a Hadron Collider, so they're the easiest things to measure, and they're nice and clean. But there aren't very many events, and also they're 2 neutrinos. It's harder to use the events. 6-jet events are tough. They've only been used very, very recently because there's lots of other backgrounds to that. So the best events for most measurements of just pure TD bar tend to be ones with 1 lepton and only 1 neutrino. Those events can be fully reconstructed, and those are the events that are used pretty much to measure the top quark mass, for example, and other properties of the top. At the tevatron. Now, of course, at the LHC, we're going to check that our understanding of the top quark is OK by studying this sort of thing. But of course, what we're really interested in is top quarks produced with other stuff. So what I've just told you here may not be entirely relevant, because our use of these different types of events may depend on what other stuff is produced along with the tops. But we're going to be very interested in identifying tops, so we'll be looking for events with what? B's and leptons and missing ET. Maybe there's some new physics model that produces top quarks plus missing energy. We'll be looking for B's, leptons, and lots of missing energy. That happens very easily in many SUSY models and other models as well. Do I have anything else to say about it? No, and I've got a few more minutes, which is good. I can start on the next thing, but let me first ask if there are any questions. What's the take-home message? That's a good question. So let me summarize what the points are. So again, what we're trying to do is be able to identify tops, bottoms, and taus because they're going to give us hints about new physics, perhaps, that involves flavor. So we want to be able, first of all, to measure what the standard model predicts for those things in detail, and, of course, look for any signs of anything new. We can't do that if we can't identify these particles. How do we identify them? We need to use special properties that they have, properties that come from the detailed physics of the standard model. And so what I've done here is remind you those special properties of the standard model which contribute to the things we actually use in the experiments. So that was the purpose of this. That, of course, will come back. The reason you should know this is that you should be confident that we do know there are certain things we can do and certain things we can't do with respect to identifying things. For example, here's something we can't do, naively. We talked about measuring Z goes to electrons. Supposing I want to measure Z goes to tau tau. Can I do it? If not, why not? Let's assume that I can identify these taus turning into these very narrow jets. Okay, so I see 2 taus. No question about that. What's the invariant mass of the 2 taus? Well, it depends how you interpret the question. What's the invariant mass of the 2 mini-jets that I measured? It's less than the Z mass because they're for those 2 neutrinos. So for electrons, we get this nice, for the Z, we would see a nice peak at MZ. But for the taus, we just sort of see a blob. You can't reconstruct a resonance in tau tau, which is a shame because what decays to tau tau sometimes? It's interesting. Higgs. 10% of light Higgs bosons decay to tau tau. Most of them decay to BB bar, but there's a lot that go to tau tau. It would be great if we could measure taus and see a resonance, but we can't. Not directly. There's a trick. If we don't have a Z produced like this, but we have our gluon, so that in the detector, look that edge on, there's a jet over here, and there's a tau here. Sorry, there's a tau here, and a tau here. And you use the fact that there are 2 components of momentum conservation, you can reconstruct the mass. Exercise. A very clever trick. Harder to use. You need to measure the missing ET to do it. There's some missing ET from this neutrino, and there's some missing ET from that neutrino. But it turns out there's enough information when you include the jet that you can reconstruct the invariant mass of the 2 taus. It uses the fact that the taus decay in this very collinear fashion. So you know the direction of the 2 taus. You just don't know the momentum. That's 2 unknowns, but you have 2 momentum conservation laws. That's enough. Okay, so this is actually going to be used for Higgs searches. That's why Higgs goes to tau tau is a search that will be done. But it's tricky because you have to use these various properties that are trickier to measure. For Z goes to leptons, all you have to do is measure those 2 leptons and you're done. For Higgs goes to tau tau, you have to measure a lot of different things. And there's background, because Z also goes to tau tau, and it's not that different in mass. So there's a whole bunch of things that make it trickier. But it's not impossible. Okay. All right. So let me say a couple of words to start the next lecture, unless there are any additional questions. Yes?
So my question is regarding the flavor-changing neutral current.
Yes.
So if you consider different processes which basically require those XCNCs, there seems to be a hierarchy between cross-sections that you can see. Some will be really, really suppressed, some will be not that suppressed.
Yes.
So in standard model, what exactly causes this hierarchy? Is that the
It's a complicated story, and I don't know if I can make sure that I answer correctly. Part of it is that particles with larger masses, obviously, relative to, let's say, the weak scale, have more opportunities to make contributions that are distinctive from the other flavors. So, for example, if you have a contribution from E's and Mu's, it may be that they're essentially equal. And because they're essentially equal, the E and mu can be treated as though they have a symmetry, and that symmetry itself may forbid the flavor-changing neutral current. The tau is still pretty light. So among the leptons, the symmetries are pretty good. On the other hand, you start to get to the bottom quark, and especially the top quark, now the flavor symmetries that rotate the 3 types of quarks into each other are starting to be violated. And so that tends to give larger contributions. But it's a complicated story because it does involve which process you're studying. For example, in KK bar mixing, no, I'm not going to say anything because I didn't review this and I haven't thought about it for a while. I'm just going to make a mistake. But there are all sorts of nice review articles on this that can add to that, give you a better answer. Another thing that is worth saying, though, is that our knowledge from experiment about the size of flavor-changing neutral currents is weaker for the 3rd generation than for the first 2. For example, mu to E gamma is something you can measure with extreme precision, and no one has seen it. So it doesn't. So we really know that mu to E gamma doesn't happen. Tau to E gamma is tougher because you have to make taus. It's easy to make mu's and measure mu's. Right? So the higher you go in generation, the less things have been studied, the more room there is. Now, what the B factories, the various actually lots of different machines that made lots and lots of bottom mesons have done, is they have searched for and not found any excesses in bottom flavor-changing neutral currents. And in the 90s, one would have said, well, there's all sorts of room for the bottom quark to be totally different from the down and strange quarks. And that would mean the top and bottom doublet, for example, to be very different. But we didn't see any effects, which tells us that the bottom doublet, the top and bottom doublet, the bottom part of it is behaving normally, which suggests if you want to build models of new physics, it may be tough to make the bottom and top quark, for example, composite. That is to say, the left-handed anti-bottom quark, which is a singlet, and the bottom-top doublet are constrained. The anti-top, the left-handed anti-top, the right-handed top, is not constrained by anything that's been done with the bottom physics. So you will find in many models, because of the structure of the standard model, that a lot of new physics gets hidden away in that anti-top, the SU2 singlet, because of the constraints from flavor-changing neutral currents. Okay. Again, an entire set of lectures on flavor-changing neutral currents and flavor physics is a worthwhile thing. And even in the TASI that I was at in 1990, John Rosner gave us 5 lectures, which are fantastic, and not entirely out of date either. Some things haven't changed. The bottom physics has hugely moved. But a lot of the old measurements are still the state of the art. So you can still learn things from, and also he was talking about what we would measure, which we now have measured. So you can still learn something from those 1990 lectures. One last question? Okay, so next time we will talk about the jets in more detail, and then we'll start moving into the actual process of looking for new physics. What are we looking for? How are we looking for it? What are the implications?